Would you believe me if I told you that right next door, in the closest star system to Earth, there might be a hidden world we've never seen? The James Webb Telescope hasn't just looked back to the beginning of time. It has actually peeked into our neighbor, Alpha Centauri, and detected a mysterious heat signal. From little red dots harboring impossible black holes to a secret lying just 4 light-years away, these are the discoveries NASA never dared to dream of. The universe is vast, but our community is close. Right now, is the sky above you light or dark? Leave your location and current time in the comments below, so we can bridge these cosmic distances together. A silent observatory, floating 1,000,000 miles from Earth, is quietly reshaping our perception of the cosmos. The James Webb Space Telescope has recently captured images of galaxies that emerged just 290 million years after the Big Bang. It has detected black holes with masses greater than their entire host galaxies and witnessed stars exploding at the very edge of cosmic time. We are now observing light that has journeyed for 13 billion years to finally reach its mirrors. These are discoveries that begin to test the foundations of our physical laws. 1,000,000 miles from our planet, a structure the size of a tennis court hangs in the void. This is the James Webb Space Telescope, the result of a $10 billion investment and 2 decades of construction. Its primary mirror is a marvel of engineering, designed to unfold like a piece of origami in the vacuum of space. The mirror's 6 hexagonal panels, crafted from beryllium and coated in a fine layer of gold, are designed to collect the faint light that departed from distant galaxies when the universe was in its infancy. Unlike the Hubble telescope, this observatory does not circle our own planet. Instead, it orbits a unique location in space, where gravitational forces achieve a perfect equilibrium. This spot is known to scientists as the second Lagrange point. From this vantage, protected by a sunshield as large as a tennis court that offers the equivalent of a sunscreen with a factor of 1,000,000, Webb gazes into the infrared portion of the spectrum. The focus on infrared is crucial because our universe is in a constant state of expansion. As light from the most remote galaxies travels across the vastness of space, its wavelengths are stretched. Ancient starlight, that began its journey as visible blue or ultraviolet light, has been pulled into the infrared range by the time it arrives at our solar system. This is a realm of light that Hubble was never able to see. Its cameras, designed for visible light, were effectively blind beyond a certain cosmic distance. Webb perceives a universe that remained hidden from its predecessor. The telescope began its mission on Christmas Day in 2021. For the next 6 months, engineers monitored its deployment with intense focus. A sequence of 1,044 steps had to be executed with absolute precision. Any single failure during this process would have doomed the entire mission. Yet, every panel unfolded without an error, and every instrument activated flawlessly. Then, Webb opened its golden eye and looked deeper into the past than any instrument ever built. Each of its observations functions as a form of time travel. When we view a galaxy that is 1 billion light-years away, we are witnessing that galaxy as it appeared 1 billion years in the past. It has taken that exact amount of time for its light to traverse the intervening space. Webb pushes this fundamental principle to its ultimate limit. The telescope is capable of capturing photons that started their journey when the universe was less than 5% of its present age. In its images, these ancient galaxies manifest as faint, reddish smudges set against the deep black of space. Their light has been traveling for over 13 billion years. We are not simply observing distant objects. We are watching the very dawn of the cosmos. Scientists had well-established theories about what the earliest galaxies should look like. They were expected to be small, dim, and structurally simple, as the universe was thought to be too young for anything more complex to have formed. Within its first week of operation, Webb shattered these expectations. The galaxies it discovered were not what was predicted. They appeared too large, too luminous, and far too mature. Some had already developed massive structures that, according to existing models, should have required billions of years to assemble. One astronomer described the findings as completely unanticipated, while another suggested the data might force a revision of modern cosmology. The standard model of the universe had predicted one outcome, but Webb was showing something entirely different. Each new image contained galaxies that stood in defiance of decades of theoretical work. Every spectrum told a story that did not conform to the accepted narrative. When your most advanced instrument reveals what seems to be impossible, the only path forward is to continue observing. What Webb discovered next was even more perplexing. In the telescope's initial deep field images, a particular galaxy appeared as just a tiny red dot. Astronomers assigned it a catalog number and continued their work. Sometime later, an analysis of the data was performed. The light from this specific galaxy had been stretched by a factor of 15, indicating it existed a mere 290 million years after the Big Bang. Given that the universe is 13.8 billion years old, this galaxy formed when reality was only 2% of its current age. It was designated JADES. For months, scientists scrutinized the data, convinced that a mistake must have been made. They rechecked every calculation and recalibrated their assumptions, but the measurements remained solid. This was no error. The galaxy known as JADES measures over 1,600 light-years across and shines with the light of newly forming stars. It is so bright, in fact, that Webb could have detected it even if it were 10 times fainter. This implies that other galaxies from this primordial era are still out there, waiting to be found, perhaps even some that formed earlier, within the first 200 million years of creation. This presents a significant problem for standard cosmology, which posits that galaxies grow slowly. The theory holds that they begin as small concentrations of matter within dark matter halos. Gravity then gradually pulls in surrounding gas, which ignites into stars. Over billions of years, these small galaxies merge and grow into the massive structures we see today. JADES does not fit this script. The galaxy is too luminous, too organized, and simply too large for its age. Computer simulations had consistently predicted that the first galaxies would be dim, chaotic, and small. JADES is none of those things. Its intense light originates from young stars, not from a central black hole, a detail that makes its existence even more puzzling. A black hole can generate immense brightness from a very compact region, but the process of star formation requires a great deal of time that a galaxy like JADES should not have had. Other early galaxies observed by Webb have shown a similar pattern of being larger and brighter than theory allows. One researcher likened the discovery to finding a fully grown adult in a place where one would expect to see a newborn. The universe, as we understood it, simply did not provide enough time for such structures to develop through conventional means. Some scientists have proposed that galaxy formation may have occurred more rapidly in the early universe. It is possible that stars formed with greater efficiency back then, or perhaps dark matter halos collapsed more quickly. While these ideas offer partial explanations, they do not fully account for the extreme nature of the observations. The galaxies are still too developed. Another potential explanation lies in what astronomers refer to as initial conditions. It may be that the Big Bang did not distribute matter with perfect uniformity. If some regions of space began with a higher density than others, galaxies could have formed faster in those areas. This, however, introduces new questions about why such dense regions would have existed and what process might have created them. In just 18 months of operation, the discovery of JADES extended our view of cosmic history by 40%. Every new galaxy found at these incredible distances adds another piece to a puzzle that seems to resist assembly. A researcher noted that such instruments are built not merely to confirm existing paradigms but to challenge them, though the exact nature of the break was unknown. And just as the scientific community was grappling with these massive early galaxies, Webb uncovered something that made the initial puzzle seem almost minor. In the contemporary universe, a consistent rule applies. For every 10,000 solar masses of stars within a galaxy, the central black hole contains roughly 1 solar mass. This ratio is observed everywhere we look. The Milky Way adheres to it, as do all nearby galaxies. It has been considered a cosmic law. Before the Webb telescope turned its gaze toward cosmic dawn, the record holder for the most distant known galaxy existed when the universe was only 570 million years old. Astronomers carefully calculated the mass contained within its stars, and then they determined the mass of the supermassive black hole at its center. The resulting numbers were completely unexpected. They revealed that the black hole's mass was equivalent to 10% of the total mass of all its stars combined. This meant that for every 10 solar masses of stellar material, there was 1 solar mass locked within the central black hole. This particular galaxy violated the established rule by an astonishing factor of 1,000. Scientists have a term for this phenomenon, an overmassive black hole, though the name hardly does justice to how extreme the situation truly is. To put it in perspective, it would be like discovering that a person's heart weighed 1/10 as much as their entire body. This is precisely the kind of proportion being observed in these nascent galaxies. The black hole is not merely a central point, it is a feature that dominates the whole system. The Webb telescope has since identified dozens more of these unusual objects. In its deep field imagery, they show up as small, reddish specks. Their distinct red hue originates from the intensely hot gas that is swirling into the black hole. As this material accelerates on its journey toward the event horizon, its temperature soars to millions of degrees, causing it to radiate immense amounts of energy. The effect is a compact, brilliant core that can easily outshine all the surrounding stars. This finding presents a profound challenge to everything astronomers believed they knew about the way galaxies evolve. Within galaxies closer to our own, the central black hole and the star population appear to grow in tandem. A more massive galaxy will host a more massive black hole, consistently preserving that 1 to 10,000 ratio. The relationship has been so reliable that entire theories of cosmic evolution were constructed around it. These early galaxies, however, display a fundamentally different kind of pattern. Their black holes seem to have developed first and grown with incredible speed. They achieved enormous masses long before their host galaxies had sufficient time to generate a large population of stars. One scientist articulated the strangeness of it by comparing it to a baby born with the heart of a giant. The proportions are simply incongruous. A central question emerges from this. How did these black holes become so large, so quickly? Two principal theories attempt to provide an answer. The first idea centers on the process of stellar collapse. When the most massive stars reach the end of their lives, they can collapse to form black holes, which can then expand by consuming nearby gas and dust. Yet, this method of growth is gradual. Even if a black hole were to feed continuously at the absolute maximum physical rate, growing from a stellar remnant to millions of solar masses within 500 million years would require an almost perfect set of circumstances. The second theory posits that some black holes were simply born large. Instead of originating from collapsing stars, they might have formed when immense clouds of primordial gas collapsed directly into black holes. Such objects, known as primordial black holes, would have started their existence with masses of thousands or even millions of suns. This path would entirely circumvent the slower, star-based formation process. Data from the Webb telescope is now lending support to this direct collapse scenario. A number of observations suggest that these huge black holes could not possibly have grown from stellar seeds in the limited time available. The implication is that they must have had a massive head start. This, in turn, introduces its own puzzle. What unique conditions in the early universe would permit a gas cloud to collapse straight into a black hole rather than fragmenting to form stars? The narrative becomes even more fascinating. These overmassive black holes are not situated randomly throughout the early cosmos. Instead, they appear to be part of a network. Astronomers charting the young universe found that the little red dots are clustered together along the cosmic web. This is the grand-scale structure of the universe, where galaxies are arranged along filaments of dark matter, much like beads on a set of invisible threads. Their placement provides a critical clue about how and when these black holes came into being. More mature galaxies tend to be found at the nodes where these filaments intersect, while less developed galaxies are scattered along the filaments themselves. The little red dots are found in very specific locations within this web. While they are not the most massive structures, they are among the most active, with their black holes consuming matter at an incredible pace. One survey focused on 7 of these little red dots from a time when the universe was 5 billion years younger than it is now. Every single one of them exhibited the same characteristic: an overmassive central black hole inside a relatively small galaxy. The uniformity of this finding is remarkable. It suggests this is not a case of a few strange anomalies, but rather a distinct class of objects from the early universe. As these black holes feed, they release powerful radiation. This energy floods into the surrounding gas, heating it and driving it away in a process astronomers refer to as feedback. In modern galaxies, this black hole feedback helps to regulate the rate of star formation. If the feedback is too strong, new stars cannot form. If it is too weak, stars form so quickly that the galaxy depletes its fuel. In these ancient galaxies, the feedback might be the very reason the galaxies themselves remained small. The massive black holes likely activated early, bombarding their environments with energy and thereby preventing the galaxy from creating a large number of stars. The black hole, in effect, may have stunted the growth of its own host. It would only be much later, after the black hole's activity subsided, that gas could cool and form stars at a more typical rate, which would eventually bring the mass ratio closer to what we observe in the local universe. But this explanation presents a timing dilemma. If the black holes form first and then halt star formation, where did the black holes themselves come from? They require vast amounts of gas to grow. If their own feedback is blasting all that gas away, it is difficult to see how they could have become so massive to begin with. The proposed sequence of events has a logical gap. Some researchers have put forward a burst scenario to resolve this. In this model, the black hole forms and undergoes an extremely rapid phase of growth, consuming huge quantities of gas before the feedback energy can build up enough to clear the area. This brief window would allow the black hole to swell to millions of solar masses. Only then would the feedback kick in, shutting down further growth for both the black hole and its host galaxy. Later, the entire system would settle into a more quiescent state. Other theories emphasize the role of mergers. When two galaxies collide, their central black holes can eventually merge, instantly creating a single, more massive black hole. In the early universe, galaxies were physically closer to one another, making such mergers a more frequent occurrence. A rapid succession of these events could potentially build up a supermassive black hole in a short amount of time. Webb has, in fact, already detected signs of merging black holes in the early cosmos, which lends credence to this idea. More recent observations have added another layer to the story. Some of these overmassive black holes are located in regions with a surprisingly low degree of chemical enrichment. Stars create heavy elements through fusion and release them when they die, enriching the surrounding gas. A galaxy that has hosted many generations of stars should therefore exhibit high levels of these elements. Yet, some of the host galaxies for these black holes show very low enrichment, indicating that few stars have lived and died there. This observation aligns well with the primordial black hole theory. If a black hole formed directly from pristine hydrogen and helium gas, it would not require prior generations of stars to exist. The low chemical signature would be a natural consequence. Confirming this, however, will demand many more observations. Each new spectrum that Webb captures adds another detail to this emerging picture. What astronomers can state with confidence is that the early universe was governed by different processes than the one we see today. And those differences, it is becoming clear, extend far beyond the behavior of black holes. A star exploded some 350 years ago. The resulting flash of light traveled outward at the ultimate cosmic speed, journeying through the vast emptiness between star systems. In the year 2025, this pulse of radiation arrived at a distant cloud of interstellar dust and gas, and the James Webb Telescope was positioned to witness what unfolded. The light penetrated the dust, illuminating it from within. Webb captured the subsequent glow in magnificent detail. The images revealed to scientists a structure that resembled the intricate knots and grain of wood. Densely packed sheets of material unveiled formations on a scale of 400 astronomical units, a distance equivalent to less than 1/100th of a light year. This represented a finer level of detail than anyone had previously known to exist inside the interstellar medium. Astronomers refer to this phenomenon as a light echo. The principle is analogous to an audio echo reverberating off canyon walls, except it involves light rather than sound. The supernova's initial burst acted as a kind of cosmic flashbulb, briefly lighting up material that would otherwise remain invisible. As this pulse of light continues to expand, it progressively illuminates more distant matter, creating an echo that appears to move through space. The focus of these observations was a light echo in the vicinity of Cassiopeia, a known supernova remnant. This remnant consists of the shattered debris from a star that exploded in the 1600s. Webb did not examine the remnant directly. Instead, its instruments were aimed at the background material being lit by that ancient detonation. This material has no physical connection to the star that exploded. It is simply unrelated interstellar dust and gas that happened to be in the right place at the right time. The fine structure came as a genuine shock to the research team. They had expected to see diffuse, formless clouds. What they discovered instead were highly organized layers. One researcher likened the formation to an onion with its many nested shells. These sheets of material seemed to be stacked one upon another, creating complex patterns. Some formations appear to be influenced by magnetic fields that thread through the cosmos, which could be aligning the dust into parallel arrangements. This discovery is significant because the space between stars is far from empty. Every cubic meter holds atoms of gas and tiny grains of dust. Most of this material gathers into enormous clouds, and it is from these clouds that new stars are born. Understanding their internal architecture helps astronomers better comprehend the mechanics of star formation. Before Webb, scientists could only study the exteriors of these vast clouds. Now, they are able to peer deep inside. The sheet-like structures that were observed measure approximately 400 astronomical units across. To offer a sense of scale, our entire solar system, including Neptune's orbit, spans only about 120 astronomical units. This means these sheets are several times larger than our own planetary system, yet they are merely small features within much larger clouds. A key question is why the material organizes into sheets instead of random blobs. Magnetic fields provide one compelling explanation. The interstellar medium is permeated by lines of magnetic force, and charged particles and dust grains tend to align themselves along these fields. Over immense timescales, this process can create elongated structures. Turbulence within the gas also plays a role, stirring the material into elaborate patterns. The researchers now believe that most dense, dusty regions in space likely share this internal character. We have simply never had the ability to look inside them before. It is probable that every molecular cloud and every star-forming region contains similar layered structures. Webb has provided us with a new template for understanding the three-dimensional architecture of interstellar space. These observations also shed light on how matter moves between stars. The sheets might serve as channels for gas flows, guiding material along specific pathways. In locations where these sheets intersect or are compressed, conditions could become ideal for star formation to begin. Understanding this helps to predict where new stars are likely to ignite. The light echo technique itself represents a novel way to probe the interstellar medium. Astronomers can wait for supernovae or other bright, transient events to illuminate different regions of space, and then use Webb to observe the structures that are revealed. Each echo provides a valuable snapshot of a different volume of interstellar space. But while Webb was studying the space between stars in our own cosmic neighborhood, it was also peering back to witness the death of stars at the farthest edges of time. On March 14, 2025, a space telescope registered a sudden flash of gamma rays. This powerful burst lasted for several seconds. Within hours, ground-based telescopes around the world pivoted to observe the fading afterglow. The light from this event told an extraordinary story. This explosion happened when the universe was only 730 million years old. The burst originated from a massive star at the very moment of its demise. Stars more than 10 times heavier than our own Sun live fast and die violently. When their nuclear fuel is exhausted, the core collapses in less than a second. The outer layers then crash inward, rebound off this imploding core, and are blasted outward in a supernova. In the most massive stars, this collapse also generates powerful jets of material that punch through the star at nearly the speed of light. These jets produce gamma rays, the highest energy form of light. When one of these jets is aimed in our direction, we register it as a gamma ray burst. This is precisely what was observed on that March morning. While astronomers had detected distant gamma ray bursts previously, this one established a new record. Its light had been traveling for more than 13 billion years. We were witnessing a star explode during the epoch of reionization, a time when the first stars and galaxies were clearing the fog of neutral hydrogen that filled the early universe. The discovery was not accidental. Ground-based observatories used spectroscopy to confirm the immense distance, but the most critical observations took place 110 days after the burst, when Webb turned its attention to the region. By then, the initial flash had subsided. What remained was the supernova itself, a slower and dimmer event than the gamma ray burst. Webb was tasked with separating the fading light of the supernova from the much fainter glow of its host galaxy. This is a technically demanding feat, as the supernova can outshine its host by a significant factor, and both appear as a single point of light from Earth. Webb's sharp infrared vision made the separation possible. The telescope successfully identified both the explosion and the galaxy that was home to the dying star. The observations revealed something unexpected. This ancient supernova bore a striking resemblance to supernovae seen in the modern universe. Astronomers compared it to a well-documented nearby supernova from 1998. Its brightness, its spectrum, and its evolution over time were a close match. Despite occurring in a profoundly different environment, the explosion followed the same fundamental physics. This finding is both comforting and puzzling. It is comforting because it suggests that the laws of physics have not changed over cosmic time. The way massive stars die today appears to be the same as how they died billions of years ago. This discovery is somewhat perplexing. Given the profoundly different environment of the primordial cosmos, where the very first stars were forged from almost nothing but pure hydrogen and helium, stars in our modern era, by contrast, are enriched with heavier elements that were synthesized inside earlier stellar generations, and the presence of these elements fundamentally influences the life cycle and ultimate fate of a star. The striking resemblance between this ancient supernova and its contemporary counterparts hints that metallicity, the proportion of heavy elements within a star, may not be as critical a factor as astronomers have long presumed. An alternative explanation is that the most colossal stars might simply follow a similar evolutionary path, irrespective of their elemental makeup. Only through additional observations of such remote stellar explosions can this scientific question begin to find a resolution. The galaxy that hosted this event also offers its own quiet insights into the early universe. It appears as a small, dim smudge of light, a target so faint it is barely perceptible even with the power of Webb. What this implies is that the cycle of massive star formation and death was well underway inside some of the universe's most diminutive galaxies. It is possible that these very galaxies were the foundational components, the building blocks that would later coalesce to create the grander structures we observe today. Discovering a supernova at such an immense distance also provides a novel method for probing the conditions of the nascent cosmos. For a fleeting moment, each of these cataclysms serves as a brilliant beacon, casting light upon its immediate cosmic neighborhood. This temporary illumination allows astronomers to analyze the gas enveloping the dying star, carefully measuring its density and chemical composition. In doing so, they can uncover the state of the interstellar medium as it existed billions of years in the past. When a supernova is accompanied by a gamma-ray burst, it offers a powerful opportunity to test our models of stellar evolution. Theoretical physicists have developed predictions for how the most massive stars ought to behave across different eras of cosmic history, and real-world observations serve to either validate or challenge those very predictions. The fact that this primordial explosion so closely mirrors modern events lends support to current stellar evolution theories, yet it also introduces a new puzzle: why environments lacking in heavy metals do not yield more pronounced differences in the outcome. But while this single star was meeting its solitary end, in another corner of the early universe, a different kind of cosmic drama was unfolding, where black holes were not alone. Upon examining Webb's images of a system designated ZS7, astronomers were immediately struck by the sight of a galaxy with two distinct, luminous cores. This particular galaxy was observed as it was just 740 million years after the Big Bang. Initially, the research team considered the possibility that they were looking at a single galaxy with a peculiar internal structure. Their perspective shifted, however, once they analyzed the system's spectrum of light. The data revealed clouds of gas moving at tremendous speeds near both of the bright points, swirling in tight orbits at velocities of hundreds of kilometers per second. Such rapid, constrained motion is the telltale signature of matter being pulled into the immense gravity of a black hole. As this material accelerates on its inward journey, it heats up to millions of degrees, causing it to radiate light at very specific wavelengths, which in turn betrays the presence of an actively feeding black hole. Remarkably, this distinct signature was present in both of the galaxy's cores. The conclusion was inescapable. ZS7 was home to two supermassive black holes, locked in a mutual orbit. This represents the most ancient pair of merging black holes ever identified. These two cosmic giants are slowly spiraling toward one another, on an inevitable course to collide and coalesce into a single, even larger black hole. It was Webb's exceptionally sharp vision that enabled the team to resolve the two black holes as separate objects. They are incredibly close, yet clearly distinct. From the ground, this pair would appear as just a single, blurry point of light, and even previous space-based observatories did not have the necessary infrared sensitivity to study such distant systems in this level of detail. Only Webb possessed the power to resolve the system and recognize it as a merger in progress. This finding carries profound implications for our understanding of how the supermassive black holes we see in the nearby universe came to be. At the heart of most large galaxies lies a supermassive black hole, and a central question has always been how these behemoths grew to masses millions or even billions of times that of our Sunday. Mergers provide one potential pathway. When two galaxies collide, their central black holes are expected to eventually sink toward the new galactic center, where they can combine. If such mergers were uncommon in the early cosmos, then black holes would have needed to grow mostly by accreting gas from their surroundings, which is a comparatively slow process. Even when consuming matter at the highest theoretical rate, it would take a black hole born from a star hundreds of millions of years to reach supermassive proportions. Identifying a merger at this early epoch, known as cosmic dawn, suggests that these events occurred often enough to provide a significant shortcut for black hole growth. The two black holes within JWST have not yet made contact. Instead, they continue to orbit one another, steadily losing energy and drawing ever closer. This loss of energy is carried away in the form of gravitational waves, subtle ripples in the fabric of space-time, first predicted by Einstein. As these massive objects circle each other, they continuously radiate these waves, which depletes their orbital energy and causes their orbit to decay. The moment the black holes finally coalesce, their collision will unleash a tremendous burst of gravitational waves into the cosmos. Future observatories designed to detect gravitational waves should be capable of sensing mergers of this scale, whereas our current Earth-based detectors are tuned to the mergers of smaller black holes occurring in the more local universe. The next generation of detectors, operating from space, will extend this reach to include supermassive black holes at very high redshifts. By detecting the gravitational waves from these ancient mergers, scientists will be able to determine the frequency of such events in the early universe. With that information, astronomers can then calculate what proportion of a black hole's growth came from mergers compared to the steady accretion of gas. This will place important constraints on our models of how black holes formed and evolved during the first billion years of cosmic time. The JWST system also serves as a window into the process of galaxy mergers in the distant past. During a galactic collision, the constituent stars, gas, and dark matter of both systems begin to interact. Individual stars very rarely collide head-on, as the space separating them is immense. The vast clouds of gas, however, do crash into one another, an event that can trigger intense bursts of new star formation. The force of the collision compresses this gas, creating pockets of material dense enough to collapse and ignite as new stars. Over time, the two galaxies will completely combine, resulting in a single, larger galactic structure. Their central black holes, however, take much longer to merge, as they must first shed their angular momentum to fall toward the new center. This momentum is carried away through complex gravitational interactions with the surrounding gas and stars, a process that causes the black holes to spiral inward over millions of years before they can finally coalesce. In terms of its stellar mass, JWST is comparable to the Large Magellanic Cloud, a small satellite galaxy that orbits our own Milky Way. It is a remarkable thought experiment to imagine the Large Magellanic Cloud hosting two supermassive black holes, each as massive as the one at the center of the Milky Way. In such a scenario, the two black holes would completely dominate the dynamics of their host galaxy, and this is precisely the situation observed in JWST. Discovering such a merger so early in the universe's timeline strongly suggests that the fundamental processes shaping galaxies and their black holes today were already at work in the distant past. Yet, another aspect of these primordial systems has long remained a source of bafflement for scientists. The light from the most remote galaxies has journeyed for such an immense duration that the universe itself has expanded considerably in the interim, and this cosmic expansion has the effect of stretching the light waves as they travel. Astronomers quantify this stretching effect using a value known as redshift, which is a number that indicates the degree to which the light's wavelength has been elongated. For instance, a redshift of 1 signifies that the light's wavelengths have doubled in length, while a redshift of 2 means they have tripled. The object known as JADES has a redshift of 14.32. The ancient light from this particular galaxy has been elongated on its long journey. Its waves stretch to 15 times their original size. What began as ultraviolet radiation departed its source only to arrive at the Webb telescope as infrared light. This profound transformation is precisely why infrared observatories are indispensable for peering into the cosmic dawn. The light has been shifted so profoundly toward the red portion of the spectrum that it has become entirely invisible to telescopes designed for visible light. To quantify such a shift, astronomers rely on a method known as spectroscopy. The Webb telescope performs this by splitting the incoming light from a celestial object into its constituent wavelengths, which generates a visual map called a spectrum. Within this spectrum, specific elements present in the galaxy leave their signatures as either emission or absorption lines at very precise wavelengths. Scientists have a fundamental understanding of where these spectral lines should be located when the light is first produced. By carefully measuring the position of these lines in the spectrum they actually observe, they can calculate the exact degree to which the light has been stretched. For the galaxies observed by the JADES program, emission lines from hydrogen that ought to be in the ultraviolet part of the spectrum are instead found deep within the infrared. The magnitude of this shift is so immense that it leaves no room for doubt. The galaxy is unequivocally from a very early epoch. The light we are now seeing began its voyage just 290 million years after the Big Bang. For more than 13 billion years since that moment, this light has been traversing a universe that is constantly expanding. This cosmic expansion also influences our perception of distance in space. When an astronomer states that a galaxy is 13.5 billion light-years away, they are referring to the light travel distance, or how long its light has taken to reach us. However, during those 13.5 billion years, the fabric of space itself has been stretching. If one could somehow pause the expansion of the universe at this very moment and measure the true physical distance to that galaxy, it would be considerably greater than 13.5 billion light-years. This is known as the co-moving distance, a measurement that factors in the expansion that has taken place throughout the light's journey. Consequently, redshift serves as a more fundamental measurement than distance alone. It provides a direct indication of how much the universe has grown since the light was emitted. A redshift value of 14, for instance, signifies that the universe has expanded by a factor of 15 since that light left its cosmic home. The wavelength of every single photon from that source has been stretched by that same factor. This stretching process has consequences beyond just changing the light's color. It also causes the light to become dimmer. Photons that arrive at Earth possess less energy than they had at their point of origin, as each one is redshifted to a longer, lower energy wavelength. In addition, these photons arrive at a slower rate because the path they must travel through space has itself expanded. The combination of these two effects makes extremely distant objects appear far fainter than they would if they were closer. The Webb telescope is engineered to counteract this dimming with its enormous primary mirror and its highly sensitive detectors. The mirror's function is to gather the maximum possible amount of light. The detectors, in turn, are cooled to just a few degrees above absolute zero, a measure that minimizes background noise and enables them to register incredibly weak signals. Even with this advanced technology, observing the most remote galaxies demands exposure times that last for many hours. The deep field observations for the JADES program, for example, required a total of more than 70 hours of the telescope's time. This represents a tremendous investment for a facility where every single hour of operation is immensely valuable. Astronomers are required to provide strong justification for such lengthy observation periods, demonstrating that the potential scientific discoveries are worth the significant allocation of resources. Uncovering the most distant galaxy ever seen certainly meets that high standard. The record for redshift is continually being pushed further back in time. Prior to the JADES survey, the most distant known galaxy had a redshift of 13.2. JADES advanced that record to 14.32. It is highly probable that even more remote galaxies exist, still waiting for their discovery. The Webb telescope has the capability to detect galaxies with redshifts as high as 20, provided they are sufficiently bright. This would correspond to galaxies that formed within the first 200 million years after the Big Bang. Locating such objects is an exceptionally challenging task. They are both rare and extraordinarily faint. The process requires astronomers to survey vast swaths of the sky with very long exposure times. Afterward, they must meticulously sift through the data to identify potential candidates, which then need follow-up observations with spectroscopy to confirm their distances. Each new record-setting discovery is the culmination of months, or even years, of dedicated work. Yet, this effort is what reveals fundamental truths about the era of cosmic dawn. The earliest galaxies were not faint objects hiding in the distant darkness. They were luminous, active, and surprisingly well-formed. They existed within a universe that was expanding in a manner that continues to puzzle scientists today. Astronomers measure the rate of the universe's expansion using a value known as the Hubble constant. This number describes how quickly galaxies are moving away from one another for a given unit of distance. The current consensus value is approximately 70 kilometers per second per megaparsec. What this means is that for every megaparsec of distance between two galaxies, their recession speed increases by 70 kilometers per second. A megaparsec is equivalent to about 3.3 million light-years. Therefore, a galaxy located 3.3 million light-years away from us is receding at 70 kilometers per second, while one at 6.6 million light-years recedes at 140 kilometers per second. This linear pattern continues as distances increase. There are two principal methods for measuring the Hubble constant. The first approach utilizes light from the cosmic microwave background, which is the residual radiation from the Big Bang itself, now stretched to microwave wavelengths. The pattern of tiny fluctuations in this radiation provides information about the composition and geometry of the early universe. From these details, cosmologists can calculate how fast the universe ought to be expanding today, arriving at a value of 67.4 kilometers per second per megaparsec. The second method involves observing supernovae in nearby galaxies. Certain kinds of stellar explosions possess a predictable intrinsic brightness. By measuring how bright these events appear from Earth, astronomers can determine their distance. When these distance measurements are combined with velocity measurements, they yield a direct value for the Hubble constant. This technique produces a result of around 73 kilometers per second per megaparsec. These two values are in disagreement. While the difference may seem small in absolute terms, it is large enough to be statistically significant, and it has persisted despite decades of refinements to both measurement techniques. This discrepancy is known as the Hubble tension. When the Webb telescope began its mission, some scientists were hopeful that it would finally resolve this tension. The thinking was that perhaps one of the methods contained a subtle, undiscovered error that more precise observations would uncover. Webb has since gathered the largest dataset ever compiled on nearby supernovae. The result of this extensive survey confirms the earlier measurements made by the Hubble Space Telescope. The local universe is indeed expanding at a rate of 73 kilometers per second per megaparsec. The tension, it turns out, is real. The question then becomes, what could possibly explain this discrepancy? One possibility is that our understanding of the early universe is somehow incomplete. The calculations based on the cosmic microwave background rely on a specific cosmological model. If that model is flawed, then the predicted expansion rate would also be incorrect. Perhaps dark energy behaves in a way we do not yet understand. Or maybe there is some unknown component to the universe that is influencing its expansion. Another potential explanation lies with the local universe itself. It is conceivable that the region of space we occupy is in some way unusual, expanding faster than the cosmic average. We might reside within what is known as a cosmic void, a vast, underdense region where the local expansion rate differs from the global one. However, detailed measurements of our local cosmic environment seem to suggest that we are in a fairly typical part of the universe. An intriguing alternative is that the universe itself has not always behaved consistently throughout its history. The cosmic microwave background provides a window into the cosmos, as it existed just 380,000 years after the Big Bang. Data from supernovae, by contrast, reveal the universe's nature over the last several billion years. If some event occurred in the vast expanse of time between these two eras to speed up the expansion, it could account for the conflicting measurements. This possibility has led some theorists to propose the existence of new physics. Perhaps gravity operates under different principles on cosmological scales than we currently understand. Another idea is that dark energy is not a constant, but a force that has actually grown in strength over cosmic time. Pursuing these concepts would necessitate a modification of general relativity, the foundational theory of gravity developed by Einstein. Scientists are understandably hesitant to take such a significant step without truly compelling proof. One potential source of error has recently been ruled out by observations from the Webb telescope. Some researchers had put forward the idea that the measurements from the Hubble Space Telescope might have been affected by a systematic instrumental bias. Webb, however, relies on completely different instruments and utilizes distinct observational methods. The fact that its results match Hubble's effectively eliminates instrument error as the reason for this tension. What remains is a profound and genuine mystery. Two of the most rigorous methods in cosmology, each honed over decades of work, are giving different answers to the fundamental question of how fast our universe is expanding. One of these methods must be flawed, or the universe itself is substantially more complicated than our current models can describe. In either case, resolving this tension will almost certainly require a new physical framework, and the puzzles extend far beyond just the rate of expansion. The very first stars to ever exist were fundamentally different from any star we see today. They were formed from pristine, unblemished gas that was untouched by any prior stellar generations. This primordial material consisted of only hydrogen and helium, along with trace amounts of lithium that were synthesized in the Big Bang. There was no carbon, no oxygen, and no iron. Nothing heavier than lithium was present. Astronomers refer to this theoretical first generation of stars as population 3. A star of this kind has never been directly observed. Every single star that humanity has ever studied contains at least some quantity of these heavier elements. And yet, cosmological theory demands that population 3 stars must have existed at some point. There had to be an origin for the first heavy elements in the cosmos. Those elements could only have come from this initial generation of stars. These primordial suns would have been incredibly massive. This is because there were no heavy elements to help the gas cool efficiently. As a result, the star-forming clouds of that era remained hot. Hot gas naturally resists the inward pull of gravitational collapse. Only the most gigantic clouds of gas could generate enough gravity to overcome this resistance and finally form stars. Simulations suggest that population 3 stars typically had masses between 50 and 500 times greater than our own Sunday stars. Of such immense size burn with incredible brilliance, but have very short lives. A star that is 100 times heavier than our own will consume its nuclear fuel in just a few million years. It then ends its life in a cataclysmic supernova explosion, which scatters its newly enriched material far out into space. The next generation of stars then forms from this enriched gas, which now contains the heavy elements that were forged inside those very first stars. The population 3 stars themselves should have disappeared billions of years ago. Their lives were simply too brief for any of them to have survived into the modern era. It is possible, however, that we could still witness them by looking far enough back in time. The Webb telescope has the ability to observe galaxies as they appeared when the universe was less than 500 million years old. This is an early enough period in cosmic history that some population 3 stars might still have been shining. Locating them is an extraordinary challenge. A single massive star is far too faint to be seen across billions of light-years of distance. Astronomers must instead search for the collective signature of many population 3 stars shining together. The spectrum of a star made of pure hydrogen and helium is different from that of a star enriched with metals. Certain emission lines in its light should be very strong, while others would be weak or entirely absent. Observations by Webb of a distant galaxy known as GNZ11 have revealed some tantalizing hints. This galaxy existed 430 million years after the Big Bang. The spectra gathered from its outer regions show powerful hydrogen emissions, with unusual ratios between the different spectral lines. This observed pattern is a close match for what theorists predict for a region where population 3 stars are actively forming. The evidence is not yet definitive, as other cosmic processes could potentially create similar spectral features. Still, the mere possibility is a source of great excitement for astronomers. If this finding is confirmed, it would represent the first ever detection of the stars that originally brought light into the dark universe. These were the objects that seeded the cosmos with the first heavy elements, which in turn made the formation of planets and eventually life possible. Population 3 stars also had a profound influence on the reionization of the universe. In the time after the Big Bang, the universe was a hot, ionized plasma. As it expanded and cooled down, electrons and protons came together to form neutral hydrogen atoms. This transition made the universe transparent, but also dark, as it was now filled with a neutral gas that absorbed most wavelengths of light. This period is known as the Cosmic Dark Ages. When the first stars finally ignited, their intense ultraviolet radiation began to ionize the hydrogen gas around them. This process created expanding bubbles of ionized gas in the darkness. As more and more stars formed, these bubbles continued to grow and eventually started to merge. In time, the entire universe became ionized once again. This period, known as the Epoch of Reionization, stands as one of the most important phase transitions in all of cosmic history. Population 3 stars were likely a crucial part of this process. Their incredible ultraviolet output would have been capable of ionizing vast volumes of the surrounding space. Early galaxies that were densely packed with these stars would have acted as powerful engines of reionization. They would have cleared away the neutral fog, allowing light to travel freely across the cosmos for the first time. Webb is now systematically hunting for these ancient objects. Large-scale survey programs are currently imaging and collecting spectra from hundreds of early galaxies. Each individual spectrum holds the potential to contain the telltale signs of population 3 stars. Even if only a small percentage of these early galaxies still host such primordial stars, the comprehensive surveys should be able to find them. Such a discovery would connect us directly to the very first chapter of cosmic history. We would be seeing the ancestors of all other stars, the original engines that transformed the universe from a state of darkness into one of light. But as scientists have searched for these first stars, they have also found objects they cannot explain at all. In Webb's deep field images, they appear as tiny, crimson points of light. They are compact, surprisingly bright, and distinctly red. Astronomers have given them the deliberately non-specific name of little red dots, a reflection of how these objects currently defy easy classification. They are found in the early universe, at redshifts between 5 and 8. This range corresponds to a time when the cosmos was between 1 and 2 billion years old. Their red color is thought to originate from extremely hot gas swirling around a central black hole. As matter spirals inward, intense friction heats it to millions of degrees. This process creates a glowing accretion disk that radiates energy across the entire electromagnetic spectrum. The particular color that we observe is determined by the gas temperature and the amount of dust that envelops the system. A heavy shroud of dust will block the shorter, bluer wavelengths of light, which makes the object appear redder to us. These little red dots are not a rare phenomenon. Extensive surveys have already identified dozens of them. They seem to constitute several % of the total galaxy population during these early cosmic epochs. Their sheer abundance has come as a great surprise to scientists. In the early universe, the sheer number of compact red objects that appeared was something no one had anticipated. What makes these bodies so perplexing is their spectrum. When astronomers separate their light into its component wavelengths, the pattern reveals a curious blend of signatures. The broad emission lines, typical of black holes, appear alongside the narrower features associated with star formation. The broad lines signify gas moving at thousands of kilometers per second very close to a black hole, while the narrow lines indicate gas traveling much more slowly in stellar nurseries. Under normal circumstances, these two kinds of signals come from different celestial sources. Active galactic nuclei, which are fueled by supermassive black holes, produce broad emission lines, whereas star-forming galaxies display narrow ones. The little red dots, however, exhibit both simultaneously. This raises a fundamental question. Are they galaxies with black holes that are unusually active? Or are they black holes surrounded by unusually intense star formation? It is also possible they are something else entirely. Their compact nature only adds to the enigma. These objects are so small they appear as mere points of light, even to an instrument as powerful as Webb. All of their emission originates from a region that is less than about 1,000 light-years in diameter. To put that in perspective, our own Milky Way galaxy stretches 100,000 light-years across. Little red dots manage to concentrate an immense energy output into a volume 100 times smaller than that of a typical galaxy. Some scientists propose that these objects are simply quasars that are heavily obscured by dust. Quasars, the most brilliant objects known, are powered by matter spiraling into supermassive black holes. If a quasar is enveloped in a thick enough shroud of dust, its visible and ultraviolet light is absorbed and then re-emitted as infrared radiation, causing the object to look both red and compact. Another possibility is that the little red dots represent a brief, transitional stage in the life of a galaxy. They might be galaxies in the midst of creating their very first supermassive black hole. In this scenario, the black hole has just ignited and is consuming gas at a furious rate, which generates the active nucleus signature. At the same time, the host galaxy is still busy forming stars, which accounts for the narrow emission lines. In time, the black hole would grow large enough for its energy feedback to halt star formation, allowing the object to mature into a conventional quasar. A third theory centers on their environment. Little red dots tend to appear in clusters, occupying specific nodes within the cosmic web's large-scale structure. This suggests their formation might depend on special conditions that are only present in these dense cosmic neighborhoods, where collisions between gas clouds or interactions among smaller galaxies could ignite both black hole growth and star formation at once. Observations from Webb are currently putting these different ideas to the test. By capturing detailed spectra from many little red dots, astronomers can measure key properties such as black hole mass, the rate of star formation, the quantity of dust, and the chemical makeup of the gas. These measurements help to distinguish between the various formation scenarios. One recent study looked at 7 little red dots from the same cosmic period. An intriguing pattern emerged. All 7 showed evidence of having overmassive black holes, with the black hole's mass accounting for around 10% of the total stellar mass. Such consistency implies that we are observing a genuine population with common traits rather than a collection of random cosmic peculiarities. The very existence of so many little red dots also places important constraints on models of black hole formation. If these objects are a common feature of the early universe, then the processes that create them must be both efficient and robust. This could lend weight to scenarios in which black holes form rapidly, either through direct collapse or accelerated accretion. Yet another puzzle lies with the host galaxies themselves. When Webb uses its extreme sensitivity to image the areas around these objects, it sometimes picks up a faint, extended glow. This reveals that the compact red core is nestled within a larger, dimmer galaxy. The host galaxy is so faint in comparison to the brilliant active nucleus that it is nearly lost in the glare. Understanding the dynamic between the dim galaxy and its luminous core is crucial for revealing how black holes and their hosts evolve together. Little red dots stand as one of the most significant surprises from Webb's first years of operation. The discovery of so many of these enigmatic objects was truly unforeseen. While each new observation adds another piece to the puzzle, a complete picture remains just out of reach. And as scientists grapple with the confusion caused by little red dots on small scales, the universe's large-scale structure presents its own set of challenges. The cosmos is not uniform. Gravity causes matter to clump together, weaving a vast network known as the cosmic web. Galaxies tend to align along filaments of dark matter, forming luminous chains that span hundreds of millions of light-years. Where these filaments cross, massive clusters of galaxies take shape. In between, the filaments are enormous, underdense regions called voids, which contain very few galaxies. This intricate structure arose from minuscule density fluctuations that were present just after the Big Bang. Regions that were slightly denser than average began to attract more matter through their gravitational pull. Over billions of years, these minor variations grew into the web we observe today. By tracing this web back through cosmic time, we can see how the structure of the universe evolved from a smooth, uniform state to the lumpy distribution we see around us. Webb is capable of seeing this structure at unprecedented distances. By mapping galaxies in the early universe, astronomers can reconstruct the appearance of the cosmic web when reality was less than 2 billion years old. Even at that early stage, the web was already in place, though in a more primitive form. The filaments were shorter and not as well defined, and the clusters were only just beginning to assemble. One recent survey conducted an extremely detailed examination of a particular patch of the sky, identifying thousands of galaxies at a range of distances. By measuring their redshifts, astronomers were able to place each galaxy at its proper location in three-dimensional space. The result was a map illustrating how galaxies were distributed at different cosmic epochs. This map shows that the cosmic web has been a feature for most of cosmic history. Even at a redshift of 8, when the universe was less than 1 billion years old, galaxies were clearly gathering along filaments. The fundamental architecture was already established. What changed over time was the thickness of these filaments and the mass of the clusters located at the nodes. Understanding this evolution is essential for constraining cosmological models. The rate at which structure grows is dependent on the amount and characteristics of dark matter and dark energy. With too little dark matter, structure forms too slowly. With too much, it forms too quickly. The observed evolution of the cosmic web serves as a critical test of these ideas. Dark matter constitutes about 85% of all matter in the universe. It does not emit, absorb, or reflect light, so we can only detect it through its gravitational influence. It is this invisible substance that forms the underlying skeleton of the cosmic web. The grand architecture of the universe is built upon an invisible scaffold of dark matter, and it is within the densest concentrations of this mysterious substance that galaxies are born. The cosmic web, therefore, traces this underlying distribution. While dark matter itself remains hidden from our direct view, its presence is revealed by the galaxies themselves. By charting the locations of these luminous islands of stars, we can indirectly create a map of the dark matter structure. It is understood that galaxies are biased indicators of this structure, as they tend to form preferentially within the most massive dark matter halos. By analyzing how galaxies cluster together, astronomers can deduce the properties of the dark matter framework that guided their formation. Our understanding of gravity and dark matter allows us to create detailed predictions of the cosmic web's structure using computer simulations. These models begin with initial conditions that match the state of the early universe and are then evolved forward through cosmic time. The outcomes of these simulations can be placed in direct comparison with observational data. A close match between the two serves as a powerful confirmation of our cosmological models. Conversely, any disagreement points to the possibility of missing physics in our theories. Recent comparisons of observations from the James Webb Space Telescope with these simulations have revealed a strong agreement on the largest scales. The overall arrangement of galaxies aligns well with what is predicted, but on finer scales, certain discrepancies begin to surface. For instance, simulations forecast a greater number of small galaxies in some areas than are actually observed, while predicting fewer in others. This hints that the processes of galaxy formation may be more intricate than our current models can fully capture. The cosmic web also exerts a profound influence on the characteristics of the galaxies within it. Galaxies situated in dense environments follow a distinct evolutionary path compared to those in more isolated, underdense regions. Crowded cosmic neighborhoods lead to more frequent interactions and mergers between galaxies. Such collisions can ignite bursts of star formation and channel vast amounts of gas toward the central black holes. In contrast, galaxies residing in cosmic voids undergo far fewer interactions, allowing them to evolve in a more tranquil manner. Observations from Webb have shown that small, red, compact galaxies, often called little red dots, are not randomly scattered, but tend to occupy very specific locations. They are found clustered in moderately dense regions along the great filaments of the web. This clear environmental preference offers vital clues about the triggers for their formation. It may be that a unique combination of an ample gas supply and frequent gravitational encounters provides the ideal conditions for the rapid growth of their central black holes. Mapping the cosmic web across different cosmic eras also allows us to track the flow of matter throughout the universe's history. We can see streams of gas traveling along filaments toward massive galaxy clusters, nourishing star formation in the galaxies they pass. Once this gas arrives at a cluster, it can be superheated by shocks and turbulence, which effectively halts any further star formation. Webb is capable of observing these dynamic processes as they unfold by studying galaxies at various positions within this cosmic network. This large-scale structure forges a direct link between the universe's smallest and largest phenomena. The individual properties of a galaxy are deeply connected to its specific address in the web, while the evolution of the web itself is governed by the fundamental cosmological parameters of the universe as a whole. In this way, the study of structure formation becomes a probe into the very nature of physics. Yet, an entirely different kind of puzzle presents itself when we examine the properties of the galaxies within this nascent web. In the modern universe, galaxies exhibit a fairly typical density. If one were to calculate the total mass of a galaxy's stars and divide it by the volume it occupies, the resulting number would fall within a predictable range for most galaxies. However, galaxies in the early universe completely defy this pattern. Measurements reveal that galaxies at high redshift are dramatically denser than their local counterparts, with some being up to 1,000 times more dense. This implies they contain a similar mass of stars within a volume that is 1,000 times smaller. The stars inside these early galaxies must have orbited in extremely tight, crowded configurations where close stellar encounters could have been a common occurrence. This discovery creates a significant paradox. If galaxies begin their lives as small, dense objects, and later evolve into the large, diffuse systems we see today, some mechanism must be responsible for puffing them up over cosmic time. Galaxies, it seems, need to expand significantly without a corresponding increase in their mass. This outcome is the opposite of what most theoretical models had anticipated, as simulations typically show galaxies growing by gaining mass through mergers and star formation, not by inflating. One potential explanation lies in the process of galactic mergers. When two galaxies collide, their individual stars are so small and far apart that they almost never hit each other, instead passing through like ghosts. The powerful gravitational interactions, however, redistribute these stars into new orbits. The resulting merged galaxy is typically larger and less dense than either of its progenitors. A history of repeated mergers over billions of years could therefore lead to a gradual decrease in the average density of a galaxy population. Another contributing element is the dark matter halo. Every galaxy is embedded in the center of an enormous halo of dark matter that stretches far beyond its visible stars. As this halo grows by accreting matter and merging with other halos, its internal dark matter distribution shifts. This change alters the gravitational potential of the galaxy, which can cause its stars to migrate outward. Consequently, the galaxy expands to occupy a larger volume, even in the absence of new star formation. The influence of feedback from supernovae and black holes also plays a significant part. Powerful winds, driven by the energy from exploding stars or from active galactic nuclei, can forcefully expel gas from a galaxy. This process effectively removes mass from the galaxy's core, weakening its gravitational pull. In response, stars move into larger, more distant orbits, which causes the overall density of the galaxy to decrease. These galaxy-scale winds have been observed in numerous systems. Some researchers initially questioned if these high-density measurements were truly real, pointing out the inherent difficulty in measuring the size of a very distant galaxy. In telescopic images, such an object appears as just a small, faint smudge. To determine where the galaxy's light ends and the dark background of space begins requires making certain assumptions about its light profile, and different assumptions can yield different sizes. This is where the James Webb Space Telescope's exceptional resolution provides clarity. It can resolve fine details in distant galaxies that were impossible for the Hubble Space Telescope to see. Measurements with Webb have now confirmed that these early galaxies are indeed far more compact than expected. The effect is genuine, although the precise density difference can vary depending on how one defines a galaxy's boundary. This evolution in density is also tied to the history of star formation. If galaxies formed the majority of their stars very early on and then ceased this activity, they would subsequently grow mainly through mergers. This would keep their stellar mass relatively constant while their size increased, thus lowering their density. However, Webb's observations show that many of these early galaxies have very high rates of star formation, meaning this scenario cannot be a universal explanation. A final consideration is the role of gas. Galaxies in the early universe contained a much higher fraction of gas compared to stars than modern galaxies do. Gas is significantly more compressible than stars, which allows a gas-rich galaxy to be much denser as the gas can be squeezed into a smaller volume. As the galaxy ages, it converts this gas into stars. Once formed, stars are not compressible in the same way, which naturally causes a decrease in the galaxy's overall density over time. Ultimately, the observed evolution of galactic density serves as a crucial test for our cosmological models. If the universe expands according to a specific metric, then the galaxies within it should evolve along a predictable path. When observations fail to align with our predictions, it points to a fundamental issue. Either the way we measure the cosmos is flawed, or the story of galaxy evolution contains chapters we have yet to read. Some alternative cosmological frameworks, for instance, propose that galaxies in the distant past should be similar in size to those we see nearby. These models, which are not accepted by mainstream astronomy, suggest a universe that either does not expand or expands in a very different manner. In this view, the redshift of distant light is caused by motion through space, not by the stretching of space itself. While these ideas remain controversial, the new measurements of galactic density provide hard data that any successful model of the universe must ultimately explain. Whatever the final answer may be, the Webb telescope has made one thing clear. Galaxies in the early universe were not simply miniature versions of their modern counterparts. Their structures and dynamics were fundamentally different, and understanding this profound transformation is the key to unlocking the secrets of how all galaxies form and evolve over cosmic time. The differences, it turns out, go far beyond just density. Consider the galaxy known as JADES 130. Located more than 13 billion light-years away, it should appear incredibly dim. The light from this distant island of stars has journeyed across expanding space for nearly the entire history of the cosmos. By the time this ancient light finally reaches the mirrors of Webb, every photon has been stretched by redshift, causing it to lose energy. The stream of photons has also been thinned out by the sheer scale of the expansion. As a rule, objects that are far away always appear fainter than those that are close. And yet, what is remarkable about JADES 130 is its brightness. It is surprisingly, even shockingly, bright. In fact, it shines with such intensity that Webb could have detected it even if it were 10 times fainter. This immediately raises a compelling question. If a galaxy this bright is so easy to find, where are all the others at similar cosmic distances? They ought to be visible everywhere. The surprising answer is that they are. The Webb telescope has been discovering a great number of luminous galaxies at high redshift, far more than pre-launch models ever anticipated. These galaxies appear to dominate the early universe in a way cosmologists had not foreseen. The era of cosmic dawn was not a dim and quiet period. It was an epoch ablaze with furious star formation. A galaxy's brightness offers a direct window into its rate of star creation. The most brilliant galaxies are those that are forming stars at a rapid pace. It is the intense ultraviolet light pouring from young, hot stars that makes a galaxy so luminous. By carefully measuring how bright a galaxy appears and then correcting for its distance and redshift, astronomers can estimate how many new stars are being born each year. In the case of JADES 130, stars are forming at a truly prodigious rate. Current estimates point to dozens of solar masses worth of new stars igniting every year. For a sense of scale, our own Milky Way galaxy currently forms only about 1 or 2 solar masses of stars annually. This means JADES 130 is tens of times more active, despite being significantly smaller. It is this high rate of star formation, concentrated within a compact volume, that generates the extraordinary brightness we observe. The galaxy's size only deepens the puzzle. Measuring over 1,600 light-years in diameter, it is considerably larger than expected for a galaxy of its age. Simulations had predicted that galaxies at this early epoch would be tiny constructs, perhaps only a few hundred light-years across. JADES 130 is several times larger, indicating it had enough time to assemble a substantial structure. Ultimately, what makes any galaxy bright is the number of young, massive stars it contains. These stellar titans burn with incredible ferocity, emitting vast quantities of ultraviolet light. A galaxy with a greater population of these young stars will naturally be more luminous. The mystery of the unexpected brightness of early galaxies, therefore, becomes a question about star formation. Why were they so remarkably efficient at creating stars? One important factor is the available fuel supply. Galaxies in the early universe were incredibly gas-rich, having not yet converted much of their primordial material into stars. With such an abundance of fuel, star formation could proceed at an accelerated rate, This gas was also pristine, composed almost entirely of hydrogen and helium, and it flowed steadily into galaxies along the filaments of the cosmic web. Another contributing element is the relative absence of heavy elements. In the modern universe, dust grains forged from these heavier elements play a role in cooling gas clouds, which helps stars to form. However, this same dust also absorbs ultraviolet light, effectively dimming a galaxy. Because early galaxies had very little dust, more of their starlight could escape unimpeded, making them appear brighter than a comparable modern galaxy that is shrouded in more dust. The feedback mechanisms that regulate star birth also seem to have been different. In nearby galaxies, powerful winds from supernovae and supermassive black holes can heat up or expel gas, preventing it from collapsing to form new stars. Early galaxies may have had weaker feedback, as their central black holes were still growing, and supernovae were only just beginning to enrich the interstellar medium. This weaker regulation would have allowed star formation to continue at much higher rates. Even so, these explanations only seem to partially resolve the brightness puzzle. When astronomers account for high gas content and weaker feedback, their simulations still struggle to produce galaxies as luminous as those being observed. A significant gap persists between our theories and the actual observations. Some researchers have proposed that the luminosity we see is not constant, but is instead boosted by a temporary starburst phase. When galaxies merge or experience a massive influx of gas, star formation can surge to rates far exceeding the long-term average. These bursts are fleeting, lasting only a few tens of millions of years. But during that time, a galaxy would appear exceptionally bright. If we happen to be observing many of these galaxies during their brief, brilliant phases, they would seem more luminous than expected. Another intriguing possibility involves the stellar initial mass function, which describes the distribution of stellar masses at the time of their birth. In the local universe, star formation typically produces a large number of low-mass stars and comparatively few high-mass stars. But if the early universe had a different recipe, one that preferentially produced more high-mass stars, then the total ultraviolet luminosity for each unit of mass converted into stars would be much higher. This would make early galaxies appear brighter without necessarily requiring a greater overall rate of star formation. Testing these compelling ideas requires detailed observations of many galaxies, and Webb is now conducting large surveys to build up the necessary statistics. By examining hundreds of early galaxies, astronomers can begin to determine whether these bright objects are rare, exceptional outliers, or if they represent the typical population of that era. The data gathered so far suggests they are indeed typical, meaning the early universe was genuinely a brighter place than our models had led us to believe. This finding carries significant implications for our understanding of reionization. Brighter galaxies produce more photons capable of ionizing hydrogen. If the early universe contained more of these luminous galaxies than previously thought, it would have generated a greater amount of ionizing radiation. This could have caused the reionization of the universe to happen more rapidly than earlier models suggested, a hypothesis that Webb's continued observations of galaxies from that era will directly test. Meanwhile, on scales vastly smaller than the cosmos, Webb has also found something extraordinary. Our closest stellar neighbor is Alpha Centauri, a system of 3 stars orbiting one another just over 4 light-years from Earth. 2 of these stars, Alpha Centauri A and B, are quite similar to our own Sun. The third member of this trio, Proxima Centauri, is a small red dwarf. For decades, this nearby system has been a source of endless fascination for astronomers. The search for planets orbiting our nearest stellar neighbors represents a profound astronomical endeavor. Proxima Centauri is already known to host a system of at least 2 confirmed worlds, one of which travels within the habitable zone where liquid water might exist on a solid surface. However, the quest to find companions around Alpha Centauri A and B has presented a much greater difficulty. The intense brilliance of these two stars generates an overwhelming glare that has long masked the faint, reflected light of any orbiting planets. For ground-based observatories, detecting such worlds around luminous, nearby stars is an exceptionally challenging task. The Webb telescope has introduced a new approach to this problem. Using its mid-infrared instrument, astronomers developed a highly specialized observing method to look directly into the radiant light of Alpha Centauri A. Their work revealed something intriguing. A faint source of infrared light located at a distance from the star roughly twice that of Earth from our Sunday. The characteristics of this faint signal are consistent with what one would expect from a large planet, possibly a gas giant. For now, this detection is considered tentative. Additional observations are required to confirm that the signal is from a planet and not from a background object or an instrumental artifact. If it proves to be real, this world would become our closest planetary neighbor outside the solar system, apart from the small worlds of Proxima Centauri. Discovering a planet at Alpha Centauri would be a monumental achievement. The star system's proximity to Earth means that future missions could one day be sent to visit it. Detailed studies of any planets there would yield invaluable insights into planetary formation and the conditions for habitability in systems similar to our own. Even the confirmation of a cold gas giant would be significant, as it would deepen our understanding of how planetary systems are structured. The observational technique created for this detection also serves to demonstrate the remarkable versatility of the Webb telescope. It was primarily designed to study the most distant galaxies in the cosmos, not bright stars in our own stellar neighborhood. Yet, through the application of ingenious strategies, astronomers can use it for both purposes. This adaptability greatly expands Webb's scientific potential and allows for surprising discoveries to come from unexpected avenues of research. Alpha Centauri A is a star that is slightly larger and brighter than our own Sunday. If it does host a gas giant, that world likely formed through core accretion, the same process that built Jupiter and Saturn. This model involves a solid core growing from the accumulation of colliding planetesimals until its gravity becomes strong enough to capture immense amounts of gas from the surrounding disk. Such a process requires millions of years to complete and a disk with an abundance of material. The potential planet orbits within the star's habitable zone, the region where temperatures are suitable for liquid water. As a gas giant, it would lack a solid surface itself. This raises the compelling possibility that the planet could host large, rocky moons, and if it does, those moons might be habitable. This scenario would mirror the systems of Jupiter and Saturn, where moons like Europa and Enceladus are known to harbor oceans beneath their icy shells. Detecting such moons would be a feat beyond even Webb's capabilities, requiring a future generation of more advanced observatories. The light from any moon would be incredibly faint, lost in the combined glare of both its parent planet and the star. Future missions dedicated to directly imaging exoplanets may have the necessary technology, likely using star shades or coronagraphs to block the starlight and reveal the faint worlds nearby. The Alpha Centauri system also functions as a crucial test case for our theories of planet formation. Our solar system has a specific architecture that resulted from the particular properties of our Sun as it formed. By studying planets around similar stars, astronomers can determine which aspects of our own system are typical and which are unusual. This provides essential context for answering whether systems like ours are common or rare throughout the galaxy. If future observations confirm this planet's existence, it will become a prime target for follow-up studies. Scientists will aim to measure its orbit precisely, determine its mass, and search for additional planets in the system. They will also look for the presence of a debris disk, which would be composed of leftover material from the planet formation era still circling the star. Webb's power of discovery extends far beyond the early universe. It is revealing the cosmos on all scales, from the most ancient structures to the planetary systems right next door. Yet, even as it finds new worlds, it has also uncovered fine details in the space between stars. The vast regions between stars are not empty, but are filled with gas and dust at extremely low densities. In some places, this material clumps together into dense molecular clouds that can collapse under gravity to form new stars. Between these stellar nurseries, thinner gas is spread throughout the galaxy. Webb's observations of a light echo from Cassiopeia A revealed that this interstellar material has an intricate internal structure. Scientists measured features as small as 400 astronomical units across. These structures appear as tightly packed sheets that are stacked in a layered arrangement. This discovery changes our fundamental understanding of how the interstellar medium is organized. Before Webb, astronomers viewed interstellar clouds as relatively smooth and featureless. They knew that turbulence stirred the gas, creating some structure, but the details remained hidden. Webb's infrared vision, combined with the light echo technique, illuminated these structures for the first time. It is now understood that these sheets are real and ubiquitous. Magnetic fields are the likely force that sculpts these sheets. The interstellar medium is ionized in many regions, meaning its atoms have lost electrons and carry a charge. These charged particles feel the influence of magnetic forces. As the gas moves, it drags magnetic field lines along with it, and over time, this interaction organizes the material into elongated structures aligned with the field. Turbulence also plays a key role. Gas in the interstellar medium is constantly in motion, energized by supernova explosions, stellar winds, and gravitational instabilities. This turbulence naturally generates structure across a wide range of scales, from the size of entire clouds down to the smallest eddies. These sheet-like structures may function as channels for gas flows. Since stars form when gas collapses under gravity, these sheets could influence where stars are born by directing how the gas moves. Regions where sheets intersect or compress might become preferential sites for star formation. Understanding these structures therefore helps predict the future evolution of the galaxy. The observations also provide crucial constraints for theoretical models of turbulence in magnetized plasmas. Simulations can predict how turbulent energy cascades from large scales to small ones. The observed structure size and orientation provide benchmarks for testing these simulations. When models align with observations, it validates our understanding of the underlying physics. Webb's ability to probe such fine structure is a testament to the power of infrared astronomy. Visible light is scattered and absorbed by dust, making dense regions opaque. Infrared light, however, can penetrate the dust, revealing what lies within. By observing at wavelengths where dust is transparent, Webb sees structures that visible light telescopes simply cannot. The technique of observing light echoes is being extended to probe other cosmic regions, as each supernova or similarly brilliant transient event illuminates a different volume of interstellar space. By studying a multitude of these light echoes, astronomers are able to assemble a three-dimensional map of the interstellar medium's architecture across the galaxy. What emerges is a far more comprehensive picture of how matter is distributed in the vast distances that lie between the stars. Knowing this structure is fundamentally important for understanding the efficiency of star formation. If interstellar gas is organized into dense, flattened sheets, for instance, the process of gravitational collapse might unfold very differently than it would within smooth, uniform clouds. These sheets could potentially fragment first into long filaments, which then subsequently break apart into the individual dense cores where stars are born. The specific hierarchy of these structures ultimately helps determine how many stars are able to form and what their resulting masses will be. And just as the Webb telescope reveals these hidden structures in our cosmic neighborhood, it continues to pioneer new methods for comprehending the universe at large. One of the most persistent challenges in all of astronomy is the measurement of cosmic distances. For stars that are relatively close, the parallax method is effective. When you observe a star from opposite sides of Earth's orbit, its position appears to shift slightly against the far more distant background. The precise amount of this apparent shift directly reveals the star's distance. This technique, however, becomes unworkable for very distant objects, as the angular shifts become too minuscule to measure accurately. For these more remote targets, astronomers rely on what are known as standard candles. These are celestial objects that possess a known intrinsic brightness. By carefully measuring how bright one of these objects appears from Earth, its distance can be calculated. Cepheid variable stars have long served as reliable standard candles for gauging distances to nearby galaxies. A remarkable relationship exists for these pulsating stars, linking the period of their pulsations directly to their luminosity. By measuring the period, astronomers can deduce the star's true brightness. For even greater cosmic expanses, supernovae offer another type of standard candle. Specifically, Type Ia supernovae exhibit a strikingly consistent peak brightness. They occur when a white dwarf star in a binary system siphons material from its companion, accumulating mass until it reaches a critical threshold and violently explodes. This explosion unleashes a predictable quantity of energy, which makes the supernova a trustworthy indicator of distance. The Webb telescope has now validated another powerful technique that uses stars at the tip of the red giant branch. Stars with low mass, like our Sun, swell into red giants toward the end of their lives. As they evolve up the red giant branch, their luminosity steadily increases. Eventually, however, they reach a maximum possible brightness and can get no brighter. This peak, known as the tip of the red giant branch, occurs at a very consistent luminosity. By identifying these red giant branch stars in a faraway galaxy and finding the very brightest among them, astronomers can establish how far away that galaxy is. Webb's exceptional sensitivity to infrared light makes it perfectly suited for this method. Red giants emit a great deal of their light in the infrared spectrum, and Webb is capable of detecting these individual stars in galaxies that are tens of millions of light years away. An even newer approach involves the use of carbon stars. These are evolved stars whose atmospheres have become enriched with carbon. In the near-infrared part of the spectrum, carbon stars display consistent colors and brightness levels, allowing them to serve as another distinct class of standard candle. Recent observations with Webb have successfully applied this method to measure the distances to several nearby galaxies. The ability to use three independent methods together provides an incredibly powerful way to cross-check results. If all three techniques yield the same distance for a particular galaxy, it builds great confidence that the measurement is accurate. A recent study employed cepheids, stars at the tip of the red giant branch, and carbon stars to measure the distances to 10 different galaxies. The results from all three methods were in agreement, producing a value for the Hubble constant of 70 kilometers per second per megaparsec. This figure is significant because it lands between the two conflicting measurements that created the ongoing Hubble tension. It is a lower value than the one derived from supernovae, yet higher than the one calculated from the cosmic microwave background. This could suggest that the tension is perhaps less severe than previously believed, or that the entire situation is simply more complex. The consensus among these multiple methods also serves to validate Webb's own measurement capabilities. Some had wondered if the telescope might have inherent systematic errors that could affect its distance estimates. By demonstrating that three completely different techniques produce consistent answers, the study affirms Webb's profound reliability. The telescope is, in fact, measuring distances with remarkable accuracy. Refining the Hubble constant is of paramount importance because it is one of the most fundamental parameters describing our universe. This single number tells us about the age, the size, and the ultimate fate of the cosmos. An accurate value places tight constraints on cosmological models and helps us predict how the universe will continue to evolve. Every improvement in its precision narrows the field of possible models. The carbon star method is still relatively new. As astronomers gain more experience with it, they will be able to refine its calibration and reduce the associated uncertainties. Future observations with Webb will measure distances to a greater number of galaxies, which will further improve the precision of the Hubble constant. When combined with measurements made at other wavelengths and with other techniques, a consistent and unified picture should eventually come into focus. But distance measurements are just one of the many tools for understanding the cosmos. Webb also continues to reveal the intricate processes by which cosmic structures form and evolve over billions of years. A supermassive black hole, for example, does not simply pull matter inward, it also propels enormous amounts of energy outward. As gas spirals down toward the event horizon, intense friction heats it to millions of degrees. This superheated material then radiates immense energy across the entire electromagnetic spectrum. The pressure from this radiation pushes against the surrounding gas, creating powerful winds that stream away from the black hole at thousands of kilometers per second. These winds are capable of reshaping entire galaxies. When a supermassive black hole is actively feeding, these outflowing winds can sweep through the host galaxy, clearing gas out of the regions where stars form. Without a supply of gas, new stars cannot be created, and the galaxy's star formation effectively shuts down. This process, known as feedback, is one of the most critical mechanisms governing the evolution of galaxies. Webb's observations are now revealing this feedback process in action in the early universe. Galaxies that host overly massive black holes for their size show clear signs of these powerful outflows. Their spectra contain emission lines with distinct shapes that indicate gas is moving away from the galactic center at extreme velocities. The fastest of these outflows have been measured at 3,000 kilometers per second, a speed high enough to escape the galaxy's gravitational pull altogether. This helps explain why early galaxies with massive black holes tend to remain small. The black hole seems to activate first, consuming gas and growing very rapidly. As it feeds, it generates a tremendous output of energy. This energy drives winds that prevent the surrounding galaxy from forming a large population of stars. The black hole, in essence, stunts the growth of its own host. Eventually, the black hole exhausts the readily available supply of gas. As the accretion rate falls, its energy output diminishes, and the powerful winds weaken. At this point, gas in the galaxy is finally able to cool and collapse, beginning the process of star formation. The galaxy then enters a period of rapid growth, building up its stellar mass. Over the course of hundreds of millions of years, a galaxy gradually expands, its growth continuing until the ratio between its black hole and its total stellar mass aligns with the values observed in our local corner of the universe. This particular sequence of development helps to explain the disproportionately massive black holes that the Webb telescope has uncovered. We appear to be witnessing these systems in a very early phase, a time when the central black hole has already achieved immense size, but the host galaxy has not yet had sufficient time to grow in proportion. If given another billion years to evolve, these galaxies would likely appear much more conventional. While their black holes would remain enormous, the collective mass of their stars would have increased to a corresponding degree. This process of feedback also has a profound impact on the surrounding intergalactic medium. Gas that is driven out of a galaxy does not simply vanish. It travels into the void between galaxies, seeding the intergalactic medium with the heavy elements that were forged deep inside stars. This enriched material can eventually be drawn back into galaxies, or can fuel the birth of stars in entirely different systems. This cyclical flow of gas, moving into and out of galaxies, forges a deep connection between the development of individual objects and the evolution of the cosmic web as a whole. To accurately reflect what we observe, simulations of galaxy formation must account for this feedback. Earlier models that did not factor in the influence of black holes made incorrect predictions, suggesting that too many massive galaxies formed far too early in cosmic history. By incorporating the physics of feedback, These simulations now produce results that are consistent with astronomical observations. The energy released by black holes serves as a regulator for galactic growth across the expanse of cosmic time. Webb is actively putting feedback models to the test by studying galaxies at various points in their evolutionary journey. Some of these galaxies exhibit active outflows of material, while others display no evidence of feedback at all. By comparing these different systems, astronomers can begin to understand what initiates feedback and how long its effects persist. These observations will help to refine our theoretical models and deepen our comprehension of how galaxies are built. Yet, even as black holes were sculpting galaxies in the primordial universe, the stars within those galaxies were also helping to clear away the cosmic fog. Shortly after the Big Bang, the universe was aglow. Protons and electrons moved freely within a hot plasma that was suffused with light. As the cosmos expanded and cooled, its temperature fell below 3,000 degrees. At this point, electrons and protons could combine, forming neutral hydrogen atoms. The universe suddenly became transparent, but it also fell into darkness. This era is now known as the Cosmic Dark Ages. There were not yet any stars to illuminate the void. Instead, neutral hydrogen permeated all of space. This gas is a highly efficient absorber of ultraviolet light, which rendered the universe opaque at specific wavelengths. Any light attempting to traverse great distances would inevitably be absorbed by the intervening hydrogen. Then, the first stars began to shine. Their brilliant ultraviolet radiation started to ionize the hydrogen gas around them, splitting the atoms back into their constituent protons and electrons. Unlike its neutral counterpart, ionized hydrogen is transparent to ultraviolet light. Each of these early stars created an expanding bubble of ionized, transparent gas. As more and more stars were born, these bubbles continued to grow until they eventually overlapped and merged. Within several 100 million years, the entire universe was once again ionized. This fundamental shift from a neutral state to an ionized one is called reionization. It stands as one of the most significant phase changes in the history of the cosmos. Gaining a clear understanding of when and how this event occurred provides essential information about the very first stars and galaxies. The Webb telescope was specifically engineered to investigate this epoch. It is observing galaxies from the era of reionization, which correspond to redshifts between 6 and 10. These galaxies existed at a time when the universe was only partially ionized. Certain areas had already been cleared by the light of earlier stars, while other regions still remained neutral. Through the study of these galaxies, astronomers can calculate the quantity of ionizing photons they generated and determine how quickly the process of reionization unfolded. A significant challenge, however, is that not all of these photons actually leave their home galaxies. Ultraviolet light can be absorbed by dust or neutral gas located within the galaxy itself. Only the photons that manage to break free into intergalactic space can contribute to reionization. Determining this escape fraction is a difficult but crucial task for understanding the entire process. Webb spectra hold important clues about these escape fractions. The ratios of certain emission lines can reveal whether ultraviolet photons are escaping or being absorbed internally. Galaxies that have high escape fractions exhibit very specific spectral signatures. By finding such galaxies, astronomers can begin to estimate what portion of early galaxies made a substantial contribution to reionization. Current observations point to the idea that most early galaxies possessed moderate to high escape fractions. This implies they were quite efficient at releasing their ionizing photons into the space between galaxies. When combined with the unexpectedly high number of bright galaxies that Webb has discovered, this suggests that galaxies alone may have been sufficient to reionize the universe. Previous theories had often suggested that more exotic sources, such as quasars or hypothetical population 3 stars, were the primary drivers of reionization. The data from Webb, however, indicates that ordinary star-forming galaxies performed most of this transformative work. The precise timeline of reionization is still a matter of investigation. Most of the available evidence suggests that the process was complete by a redshift of 6, which is about 1 billion years after the Big Bang. However, exactly when it began and the duration of the process remain open questions. Did reionization occur rapidly, over just a few 100 million years, or was it a much slower process that stretched out over 1 billion years? Observations from Webb are helping to constrain this timeline by measuring the fraction of neutral hydrogen at different redshifts. This allows astronomers to map the progression of reionization through time. Initial results suggest that the process gained momentum around a redshift of 8. Before this point, progress was slow, but afterward, the last pockets of neutral hydrogen vanished quickly. One of the remaining puzzles concerns the topology of reionization. Did the bubbles of ionized gas expand uniformly in every direction, or did their growth follow the underlying structure of the cosmic web? Simulations tend to predict that ionized zones would have expanded preferentially along the filaments where galaxies are clustered together. This would mean that the great voids of space remained neutral for a longer period. To test this, it is necessary to map both the ionized regions and the distribution of galaxies at the same time. Webb is now beginning to generate these kinds of maps. Large-scale surveys are imaging and collecting spectra from thousands of galaxies across vast swaths of the sky. When this data is combined with measurements of the ionization state of the intergalactic medium, it reveals how reionization played out in 3 dimensions. The picture that is emerging is one of a patchy and complex process that varied considerably from one region to another. Curiously, some of the very tools that allow us to study the era of reionization are provided by an unexpected aspect of the cosmos itself. Einstein's theory of general relativity predicts that mass has the ability to warp spacetime. Light that passes through this warped spacetime must follow curved trajectories. When a truly massive object, like a cluster of galaxies, is positioned between our vantage point and a more distant galaxy, the cluster's immense gravity can bend the light from the background source. This bending effect can act as a natural magnifying glass, causing the background object to look brighter and larger than it otherwise would. Astronomers refer to this phenomenon as gravitational lensing. This phenomenon functions as a cosmic lens, amplifying light from faraway sources that would normally be too dim for observation. The Webb telescope methodically leverages gravitational lensing to peer at the most remote galaxies in the cosmos's infancy. By targeting immense clusters of galaxies, Webb can see objects located far beyond them, their light amplified by 10 or even 100 times. A recent observation, for instance, focused on a cluster known as Abell S1063. This colossal gathering of galaxies is situated 4.5 billion light-years from Earth. The immense gravity of the cluster warps the light from galaxies behind it, stretching their images into arcs or creating several copies of the same object. In just one frame, Webb was able to capture hundreds of these warped background galaxies. A number of these lensed objects hail from an era when the universe was not yet 1 billion years old. Were it not for the cluster's magnifying effect, these ancient galaxies would remain entirely invisible. Even with Webb's unparalleled sensitivity, a direct view would reveal nothing at all. This gravitational lensing effect transforms an impossible observation into a reality. The technique also enables a much more detailed examination of individual galaxies. When an object's light is amplified 50-fold, features that would typically be too small to distinguish suddenly come into focus. This allows astronomers to map out where stars are forming within the galaxy, pinpoint specific star clusters, and measure characteristics that would otherwise demand even more powerful telescopes. In one particular galaxy viewed by Webb through a cosmic lens, 10 separate star clusters were identified. Every one of these clusters marks a location where a collapsing cloud of gas gave birth to stars at roughly the same time. The intriguing detail is that the clusters are of varying ages, which suggests that star formation happened in distinct episodes instead of at a steady pace. Such a granular view is only possible because the gravitational lens amplified the galaxy's light sufficiently for its internal components to be resolved. The degree of this magnification is directly related to the alignment of the object. If a distant galaxy is positioned perfectly behind the very center of the lensing cluster, the amplification effect can be truly immense. Even a slight offset from this perfect alignment results in less magnification, but the boost is still substantial. To determine the precise magnification for every background object, astronomers create models of how mass is distributed throughout the cluster. The phenomenon of gravitational lensing also provides valuable information about the lensing object itself. The specific way light is distorted is a direct consequence of how mass is spread throughout the cluster. By carefully studying the shapes and locations of the lensed galaxies, scientists can create a map of the cluster's total mass, which includes its significant dark matter component. This method offers an alternative way to measure the properties of dark matter. In certain cases, these massive clusters can create several images of a single background galaxy. This happens because light from the distant galaxy travels along different routes around the cluster, reaching our planet at slightly different moments and from different apparent directions. Astronomers can therefore observe the same galaxy appearing in 2, 3, or sometimes even more places in the sky at once. A comparison of these multiple images allows them to test the principles of general relativity and to define the cluster's mass distribution with remarkable accuracy. The Webb telescope has already pointed its mirrors at dozens of these massive clusters, using them as natural gravitational lenses. Every one of these observations uncovers hundreds of magnified galaxies in the background. The collective effort is building a dataset containing thousands of exceptionally remote galaxies, a great many of which are amplified enough to allow for in-depth analysis. This growing collection of data is profoundly changing our understanding of how galaxies formed during the universe's first billion years. An especially potent technique involves pairing this lensing effect with spectroscopy. Webb can capture the spectra from these magnified galaxies, which allows for measurements of their chemical makeup, their rate of star birth, and their ionization state. The amplification is what makes it feasible to perform spectroscopy on galaxies that would otherwise be far too dim for such an analysis. These measurements are yielding unparalleled insights into the characteristics of average galaxies during the era of reionization. What is emerging is that some of these lensed galaxies display quite unexpected features. One such galaxy manifested as a stretched-out arc in Webb's images of a massive galaxy cluster. Gravitational lensing had both elongated and amplified its light. Because of the way it looked, astronomers gave it the nickname the Firefly Sparkle. Upon closer inspection, a remarkable discovery was made. Within this single galaxy were 10 separate, bright clusters of stars, each one clearly distinguishable in the telescope's images. This particular galaxy existed approximately 600 million years after the Big Bang. This was a time when the universe was less than 5% of its present age. Most other galaxies seen from this early epoch simply look like single, compact smudges of light. The Firefly Sparkle, however, revealed a clear internal structure. Its star clusters were visible as distinct, bright points organized into a line. An analysis of each cluster's properties showed that they possessed different ages and masses. Some of them held young, hot stars that were only a few million years old, while others were home to slightly more mature populations of stars. The mass of these clusters varied, ranging from a few thousand to several 100,000 solar masses. In total, they added up to about 10 million solar masses worth of stars. For a galaxy, this total amount of stellar mass is surprisingly small. Our own Milky Way, for comparison, contains more than 100 billion solar masses in stars. The Firefly Sparkle has less than 1/10,000th of that amount. And yet, This diminutive galaxy may offer a glimpse of what the Milky Way itself looked like at a comparable point in its history. Both its age and its mass align with predictions for our own galaxy's nascent stages. This finding supports the idea that enormous galaxies such as the Milky Way were assembled gradually from much smaller precursor systems. The Firefly Sparkle is not a completed galaxy. Instead, it appears to be a fundamental building block, a proto-galaxy still in the process of coming together. Over the course of billions of years, systems like this one would merge with others, eventually growing into the large-scale galaxies that populate the modern universe. Its 10-star clusters offer a remarkable snapshot of star formation as it was happening. Each individual cluster was born from a collapsing cloud of gas. The observation that they are of different ages reveals that the process of star birth was not a single event. It seems to have happened in distinct bursts, with millions of years separating each episode. Gas would gather within the galaxy, igniting a wave of star formation, and then perhaps this new activity would heat up or expel the remaining gas, putting a pause on star birth until more material could arrive. This kind of episodic star formation could be a common feature among the universe's earliest galaxies. Material is thought to flow into a galaxy intermittently along the filaments of the cosmic web. When a new supply of gas arrives, it can set off a flurry of star formation. The energy and radiation from these newborn stars, a process known as feedback, then heats the surrounding gas, temporarily halting any further star formation. This cycle would then repeat itself each time a new accumulation of gas occurred. Without the aid of gravitational lensing, a detailed study of the Firefly Sparkle would have been entirely out of the question. A magnification factor of about 30 made the galaxy bright enough for Webb to distinguish its individual star clusters. The discovery is a testament to the power of uniting the phenomenon of gravitational lensing with the advanced capabilities of the Webb telescope. Working in concert, they effectively provide a microscope for peering into the early universe. Other galaxies viewed through these cosmic lenses are revealing similar patterns of clustered star formation. It seems that a great number of young galaxies give birth to stars not in a uniform way, but rather in concentrated pockets of activity. This clumpy mode of star formation is likely a signature of the chaotic environments within the gas reservoirs of the early universe. Within these turbulent expanses, instabilities cause the gas to break apart into dense knots, each one capable of forming its own brilliant cluster of stars. The intriguing possibility is that these clusters themselves represent the forerunners of globular clusters, the ancient, spherical collections of stars that orbit most large galaxies in the present day. Globular clusters are immense, containing anywhere from hundreds of thousands to millions of stars packed into regions only a few dozen light-years wide, and their advanced ages confirm they were born in the universe's youth. The star clusters within the Firefly Sparkle galaxy, for instance, possess comparable masses and could very well evolve into structures that resemble the globular clusters of our own Milky Way. By studying galaxies like Firefly Sparkle, astronomers are able to link the distant past with the present, gaining a deeper knowledge of how small proto-galaxies assembled themselves and ignited their first stars. This work helps us understand how vast systems such as the Milky Way ultimately came into existence. In a very real sense, we are witnessing our own cosmic history being written in the ancient light of these objects. And yet, at the same time these galaxies were being constructed from star clusters, the essential raw materials for planets and for life were also being forged. Stars are born from the gravitational collapse of immense clouds of gas and dust. As such a cloud spins, it gradually flattens into a disk. Deep within the center, the star ignites, while the surrounding disk holds all the material that will one day coalesce into planets, moons, asteroids, and comets. A careful analysis of this disk's composition can therefore reveal the specific building blocks available for the process of planet formation. The Webb telescope observed one such young stellar system, and made a remarkable detection of crystalline water ice within its disk. This particular form of ice is defined by a regular, ordered molecular structure, much like the ice in a household freezer, which distinguishes it from amorphous ice, where water molecules are arranged in a random, disorganized fashion. The very presence of crystalline ice is a clue, indicating that specific conditions of temperature and pressure exist within the disk. This ice is situated far from the central star, residing in the frigid outer regions where temperatures fall well below freezing. Webb's spectrum of the system displayed unmistakable absorption features at particular infrared wavelengths, a clear and unambiguous signal that perfectly matched the signature of crystalline water ice. The disk, it turns out, is rich with this ice in the very zone where giant planets are thought to emerge. This discovery is significant because water is considered essential for life as we currently understand it. Rocky planets that take shape in the inner disk begin their existence completely dry, as the temperatures there are far too high for ice to survive. Water must therefore be delivered to them at a later time, likely by comets or asteroids that originally formed in the icy outer disk and subsequently migrated inward. The ice detected by the telescope represents the vast reservoir that could eventually supply these inner rocky worlds with water. Giant planets also depend on water ice for their formation. According to current models, worlds like Jupiter and Saturn began as icy cores that grew massive enough to gravitationally capture the hydrogen and helium gas around them. These cores were assembled through the collision of countless icy planetesimals, which are solid objects ranging in size from meters to hundreds of kilometers. The abundant ice found in this disk provides precisely the kind of material needed to fuel this process. The crystalline structure of the ice also tells a story about the disk's history. Amorphous ice is what typically forms when water vapor freezes very quickly. For crystalline ice to appear, the freezing process must either be slow or there must be a subsequent period of warming that gives the molecules time to rearrange themselves into an ordered lattice. Finding crystalline ice, therefore, suggests that the disk has undergone some form of thermal processing, perhaps due to shock waves or radiation emanating from its central star. The observations were specifically targeted at a disk orbiting a star quite similar to our own Sun, a detail that makes these findings directly applicable to understanding the formation of our solar system. If the early solar nebula was similarly rich in ice, then the process Webb is now observing might be a direct reflection of what occurred 4.6 billion years ago as our own planetary system was born. Other disks viewed by Webb are revealing similar features, which suggests that crystalline water ice is a common component of planet-forming disks. It appears that most planetary systems likely begin with access to substantial quantities of water during their formation. This finding increases the probability that rocky planets located in habitable zones could acquire the water necessary to potentially develop conditions suitable for life. The quantity of ice is just as important as its presence. With too little ice, giant planets might fail to form at all. Conversely, with too much ice, the disk could fragment into multiple competing cores. Webb's ongoing measurements of ice abundance across numerous disks will help determine if there is a typical amount, or if it varies greatly from one system to another. Beyond water, these disks contain other types of ices as well. Carbon dioxide, methane, and ammonia all freeze at the temperatures found in the outer regions of a disk, and Webb has successfully detected these compounds in several systems. The specific mixture of these different ices has a profound effect on the composition of any planets that form. A planet that coalesces from ice-rich material will have a fundamentally different chemistry than one that forms from rock-rich material. These observations create a powerful link between star formation, planet formation, and the field of astrobiology. The ices present in a planet-forming disk dictate the inventory of available raw materials. The planets that eventually emerge inherit their compositions directly from this disk. This is the pathway by which rocky planets in habitable zones might acquire not just water, but also atmospheres and organic compounds. It is conceivable that some of those worlds could one day harbor life. Webb is systematically cataloging these ingredients across a wide array of stellar systems. By the conclusion of its mission, astronomers expect to have a statistical grasp of how common different disk compositions are, which will in turn constrain theories of planet formation and help predict the kinds of planetary systems that exist throughout the galaxy. And while Webb investigates the birth of new systems, it also continues to monitor the deaths of ancient stars. One observed gamma-ray burst lasted for a mere 8 seconds. In that brief window, it unleashed more energy than our Sun will produce over its entire 10 billion-year lifespan. The cataclysmic explosion launched jets of material outward at 99.99% of the speed of light. Because one of these jets happened to be pointed toward Earth, detectors around the globe registered the brilliant flash of light. This particular burst originated in the very early universe, its gamma rays having traveled for more than 13 billion years before finally reaching our planet. By the time Webb was able to observe the afterglow, the explosion itself was already an event of ancient history. Nevertheless, the observation yielded precious details about how stars died during the first billion years of cosmic time. Gamma-ray bursts are generally classified into two types. Short bursts, which last less than 2 seconds, are known to come from the merger of two neutron stars. Long bursts, lasting more than 2 seconds, are the death cries of collapsing massive stars. The 8-second burst that Webb studied fell squarely into the long-duration category, indicating that a massive star had reached the end of its life. The underlying mechanism is known as core collapse. When a star more than 20 times heavier than our Sun depletes its nuclear fuel, its core can no longer generate the pressure needed to support itself against the immense crush of gravity. The core then catastrophically collapses, forming a black hole. As material spirals inward toward a black hole, it organizes into a swirling structure known as an accretion disk. From this disk, powerful magnetic fields channel and eject jets of matter, launching them at right angles to the disk itself. These focused streams punch their way through the body of the collapsing star, ultimately emerging from the stellar surface at relativistic speeds. Within these jets, the intense energy heats the material to billions of degrees, a process that generates gamma rays. As this jet travels outward into space, it gathers the surrounding material, which creates a shock wave that radiates light across the entire electromagnetic spectrum. Webb was able to observe this particular burst across multiple wavelengths. Within the infrared spectrum, Webb detected the distinct emission lines that serve as signatures for heavy elements. The spectral data clearly showed the presence of silicon, oxygen, and iron. These are elements forged deep inside the dying star through nuclear fusion, which were then cast out into the cosmos during the explosion. In essence, Webb was analyzing the star's internal composition as it was scattered across space. The discovery of these heavy elements in the spectrum is significant because it confirms that even stars in the early universe were capable of producing them. While this might now appear to be a simple conclusion, it was not a certainty. It was plausible that stars with very low metallicity might have died in a different manner, perhaps without creating such a rich supply of heavy elements. The fact that this ancient burst displays an elemental enrichment similar to that of a modern supernova suggests that the fundamental physics involved have remained consistent over cosmic time. Gamma-ray bursts also provide a unique opportunity to probe the intergalactic medium. The light from such a burst must travel through the vast expanses of gas that lie between the explosion and Earth. This intervening gas acts like a filter, absorbing specific wavelengths and leaving behind an imprint on the spectrum. By studying these absorption lines, astronomers can learn about the composition and density of intergalactic gas from billions of years ago. These observations showed absorption from neutral hydrogen, which indicates the burst occurred either during or very near the end of the era of reionization. This tells us that some neutral hydrogen was still present along this particular line of sight. Such a finding helps constrain both the timing and the location of reionization's completion. By observing different gamma-ray bursts in various parts of the sky, a more complete map of reionization's patchy nature can be assembled over time. Events like these gamma-ray bursts are exceptionally rare. A typical galaxy might experience only one every million years. Yet, across the vastness of the observable universe, hundreds of them occur each day. The primary challenge lies in detecting them quickly and pointing a telescope before their afterglow completely disappears. Ground-based telescopes can send an alert to Webb just minutes after a detection, which allows for rapid follow-up observations. This ability to react swiftly highlights Webb's operational flexibility. The telescope has the capacity to pause its scheduled programs to observe these transient, time-sensitive events. For gamma-ray bursts, this speed is absolutely critical. The afterglow diminishes very quickly, often becoming too faint to detect within just a few days. To capture meaningful data, Webb needs to begin its observations within a matter of hours. Every single gamma-ray burst observed at a high redshift deepens our knowledge of how massive stars died in the early cosmos. The collection of these observations is steadily growing. In just a few years, Webb is expected to have observed dozens of these distant bursts. This will provide valuable statistics on their characteristics and the environments in which they occurred. Ultimately, this work will reveal how the deaths of the very first massive stars enriched the universe and set the stage for subsequent generations of star formation. Yet the discoveries are pushing even deeper into cosmic history. Every few months, it seems astronomers announce a new record for distance. The most distant known galaxy is a title that is constantly being passed to a new, more remote object. Each new record holder represents an earlier moment in the universe's timeline, a step closer to the Big Bang. This steady progression demonstrates how Webb is methodically pushing back the frontier of observable time. For several months, the JADES program held the record with a galaxy at redshift 14.32. Then, another galaxy was confirmed at a redshift of 14.5. A few months after that, a candidate emerged at a potential redshift of 16. While spectroscopic confirmation for this latest find is still pending, its reality would place its formation just 250 million years after the Big Bang. One might wonder why this record continues to be broken. A part of the answer is that Webb is still in its early years of operation. Astronomers are actively analyzing the wealth of data from its first few years. As they meticulously work through these observations, they continue to uncover fainter and more distant objects. The deepest images of the cosmos require exposure times lasting for tens of hours. Not all of the planned deep fields have been observed yet, with more scheduled for the future. Improving technology also plays a crucial role. The techniques for analysis are refined as astronomers become more familiar with the nuances of Webb's data. Machine learning algorithms are now used to scan images, flagging potential high redshift galaxies that a human observer might overlook. Spectroscopic follow-up is then used to either confirm or reject these candidates, making the entire process increasingly efficient. There is also an element of statistical inevitability at play. If bright galaxies are found to exist at redshift 14, it is highly probable that even brighter ones exist at redshift 15. Galaxy formation is a continuous process, and the very earliest examples are simply the most difficult to find. If you search a large enough volume of space, you are bound to discover them, and Webb is conducting that search. Of course, this journey back in time cannot continue indefinitely. Eventually, we will reach the epoch when the first stars had yet to form. Before a redshift of around 20, no stars existed. The universe was simply too young. To look beyond redshift 20 is to peer into the cosmic dark ages, a time when space was filled only with neutral hydrogen. Webb might be able to detect a faint emission from this hydrogen, but it will not find any galaxies. The region between redshift 14 and 20 remains largely unexplored territory. Webb has successfully found galaxies at 14, and theorists predict that galaxies should have begun forming by redshift 15 or 16. The gap between what has been predicted and what has been observed is steadily closing. It is very likely that within the next few years, Webb will discover galaxies within this range, extending our view to encompass 98% of all cosmic history. Every record-breaking galaxy offers new insights. Its brightness can tell us about its star formation rate. Its spectrum reveals its chemical makeup. Its size provides clues about how cosmic structures assemble. Taken together, these measurements help constrain our models of galaxy formation. Each new discovery either reinforces our current predictions or forces us to revise them. Some of these early galaxies appear surprisingly normal. They are forming stars. They contain a measure of heavy elements, and their sizes are consistent with existing models. Others, however, are extreme outliers, appearing too bright, too massive, or too chemically enriched. These unusual galaxies are often the most fascinating because they challenge our current understanding. They hint at physical processes that we do not yet fully comprehend. These record-holding galaxies also capture the public's imagination. There is a deep fascination with seeing light that has traveled from near the dawn of time. Images that show galaxies from the first few 100 million years of the universe make the abstract idea of cosmic history feel more tangible. You are witnessing photons that have been on a journey for over 13 billion years just to reach us. But beyond these distance records lies a more profound mystery about the universe itself. The cosmos is not merely expanding, that expansion is accelerating. Galaxies are receding from one another more rapidly today than they were billions of years ago. Some unknown influence is pushing space apart with a force that seems to increase over time. Astronomers refer to this mysterious force as dark energy. The discovery of dark energy traces back to the late 1990 seconds, emerging from observations of supernovae in the distant universe. By carefully measuring the apparent brightness of these stellar explosions, astronomers could calculate how far away they were. When these distances were compared with the object's redshifts, an unexpected picture emerged. The rate of the universe's expansion was actually increasing. For the first several billion years of cosmic history, the cosmos had been decelerating, its expansion held in check by the mutual gravitational pull of all matter. A fundamental shift occurred around 6 billion years ago, when dark energy's influence became dominant, initiating a new era of accelerating expansion. The Webb telescope's observations served to both confirm and refine these pivotal findings. By studying a greater number of supernovae at even higher redshifts, Webb extends our measurements of this cosmic expansion history further back into the past. The data it gathers show that dark energy has been present for many billions of years, consistently driving the acceleration. What, then, is this mysterious dark energy? The simple truth is that no one knows for certain. The most straightforward explanation suggests it is an intrinsic property of space itself. Einstein's equations of general relativity permit the existence of a cosmological constant which represents an energy density that remains uniform even as space expands. This implies that as the universe grows larger, the amount of dark energy also increases, simply because more space exists. The total energy of the cosmos grows, which in turn drives an ever faster expansion. This concept seems to challenge the law of energy conservation, and in a way, it does. However, general relativity allows for this because the conservation of energy operates differently within the context of curved spacetime. The very expansion of space can generate or remove energy without violating the governing equations, and dark energy appears to be one manifestation of this peculiar behavior. A primary objective of modern cosmology is to precisely measure the properties of dark energy. A key question is whether it is truly a constant or if its strength changes over time. If it does evolve, the rate of that change would place important constraints on various theoretical models. Webb's observations provide crucial data points from different epochs of cosmic history, allowing us to track how dark energy has behaved across billions of years. Current measurements indicate that dark energy has been remarkably stable. Its density shows no significant variation as the universe has evolved. While this result aligns with the simplest models, it leaves the fundamental nature of dark energy a profound mystery. A cosmological constant fits the observational data well, but it fails to explain why it exists or why it possesses the specific value we measure. Alternative theories propose a different view, suggesting that dark energy is not a constant property of space, but rather a dynamic field that evolves. Certain models predict that its influence should have been stronger or weaker in the universe's earlier stages. Webb's precise measurements are designed to test these very predictions, though so far, no clear deviation from a constant has been found. The ultimate fate of the universe is tied to the nature of dark energy. If it continues to be a constant, the expansion will accelerate indefinitely. Galaxies beyond our local group will recede from us with increasing speed, eventually moving away faster than their light can travel toward us. They will ultimately vanish beyond our cosmic horizon, lost to us forever. The universe will grow progressively darker and emptier as the last stars exhaust their fuel with no new ones to replace them. Should dark energy increase over time, the acceleration could become so extreme that it would eventually tear apart galaxies, stars, and even individual atoms. This scenario, called the Big Rip, would destroy all cosmic structure, though current measurements provide no evidence that this will occur. Conversely, if dark energy were to weaken, the expansion might one day slow, stop, and reverse. Gravity would regain control, pulling all of creation back together in a big crunch. The universe would collapse into a singularity, perhaps giving rise to a new Big Bang in a cyclical model, though this idea is speculative and not supported by current data. Webb contributes to these studies by delivering precise measurements of cosmic expansion at different times. When combined with data from other telescopes and experiments, these measurements will help reveal whether dark energy is constant or if it evolves. Understanding its nature remains one of the deepest questions in all of physics. Yet, for all of its incredible power, the Webb telescope has its limits. It is the most powerful observatory ever constructed by humanity, but it cannot see everything. There are boundaries to its vision. Some objects are too faint, others are too remote, and some emit light in wavelengths Webb is not designed to detect. The initial 200 million years following the Big Bang, for instance, remain mostly veiled from our view, situated just beyond the edge of Webb's reach. Galaxies from this primordial epoch would have redshifts greater than 20. Their light has been stretched so profoundly into the infrared spectrum that even Webb's sensitive instruments struggle to capture it. These first galaxies would also have been small and dim, having had little time to form great numbers of stars. Detecting them would demand exceptionally long exposure times and likely the aid of gravitational lensing for natural magnification. Technically, Webb does have the capability to find galaxies at a redshift of 20, provided they are sufficiently bright. An object's brightness, however, depends on its mass and its rate of star formation. Early simulations predicted that the first galaxies would be tiny, with masses of only a few million times that of our Sun. Such faint objects would be far beyond Webb's ability to see without extraordinary lensing effects. There is a hopeful possibility, however, if the first galaxies produced stars more efficiently than these models suggest. This is plausible, as early galaxies have consistently proven to be brighter than originally expected. If that trend holds true for even earlier times, then galaxies at a redshift of 20 could indeed be within reach. Another significant challenge at these extreme redshifts is contamination. It becomes increasingly difficult to distinguish genuine high redshift galaxies from other celestial objects. For example, certain types of cool stars within our own Milky Way can mimic the colors of these very distant galaxies. Spectroscopy can tell them apart, but acquiring spectra for the faintest candidates requires a tremendous investment of telescope time. The James Webb Space Telescope is expected to operate for a minimum of 10 years, and potentially longer if its fuel and instruments hold up. Throughout its mission, it will conduct ever deeper observations, pushing humanity's vision closer to the epoch of the first stars. Future telescopes may one day peer beyond what Webb can achieve, but for now, it defines our cosmic frontier. What could possibly surpass Webb? Larger ground-based telescopes equipped with advanced adaptive optics are currently under construction. These will offer greater light-collecting power in certain wavelengths. A major limitation, however, is that Earth's atmosphere absorbs a great deal of infrared light, which curtails ground-based infrared astronomy. For observing the most distant galaxies, space-based infrared observatories remain indispensable. The subsequent generation of observatories in space is currently in the conceptual stages. These ideas include telescopes with mirrors twice the diameter of Webb's or vast arrays of telescopes working in concert. Such facilities could extend our observations to a redshift of 25 or even further, potentially imaging the very first individual stars, but their launch is still decades away. In the meantime, Webb is fundamentally transforming our understanding of the cosmos. What's remarkable is how each observation brings something unforeseen. We find black holes that seem too massive for their galaxies, and galaxies that shine too brightly for their early age. The birth of stars proceeds in ways our models failed to predict, while cosmic structures emerge sooner than we thought possible. These findings do not shatter cosmology. They broaden its horizons. It seems our theories were perhaps too simple, our predictions too modest. The universe is revealing itself to be infinitely more intricate and layered than we had conceived. The Webb telescope shows us the cosmos as it is, and our scientific framework must now evolve to embrace this reality. We are truly living in a golden age of astronomy. Never in human history have we witnessed the early universe with such breathtaking clarity. For the very first time, we can watch as galaxies assemble just after the Big Bang. We are now able to probe the depths of stars billions of light years from home or examine the internal architecture of distant stellar nurseries. The James Webb has uncovered the true measure of the universe, and what it shows is a cosmos vaster, stranger, and more magnificent than anyone ever anticipated. Every week seems to deliver new insights. Each new image challenges something we believed we understood. The cosmos has not yet yielded all its secrets. The telescope will continue its journey, pushing deeper into space and further back in time, showing us wonders we have yet to even dream of. This story is not ending. This is simply its beginning. Webb has opened a portal to the cosmic dawn, and we are still learning to interpret the view. For 13.8 billion years, the universe waited to be seen. Now, finally, we are looking back to the very edge of time,